Okay, I'm just going to run through the solutions to the mechanics exam if you guys needed any help with these questions. So each video I'll just do one question, so obviously you can just then look at the ones that you needed. So question 1 was the one about the bumper boats. So it says she jumps at 2 meters per second onto a bumper boat that's drifting past her, and that has a speed in this direction of 0.5 meters per second. It tells you about the mass of the bumper boat, but the first question just says draw a labelled diagram showing how the momentum vectors add together. So when you're thinking about momentum vectors, you've just got to think about what direction the things are moving in and how you can actually represent that, because remembering that we can't join vectors tail to tail or head to head. So we've got Alex here, and remembering that we've got momentum vectors. I think for some of you, you'd actually drawn vectors that weren't momentum vectors, and they needed to be labelled as well. So across the bottom, we've got Alex. Okay, so we've got Alex's momentum across here, and obviously that momentum is going to be her mass times her acceleration times her velocity. So you could have written this in. So she's got a mass of 48 kgs multiplied by her velocity, which is 2 meters per second. So we could have added that in as well. And then we've got the bumper boat's momentum, and that's going in this direction. So head to tail, we can just join those as they are. So here we've got the momentum of the bumper boat, and that's going to be the mass of the bumper boat times by its velocity. Okay, and you put those in if you want to. So if we're starting with Alex, we're going from the start where we started with Alex to the end of the bumper boat's momentum vector, and so the total momentum will be given to us by the resultant vector here. Okay, so if you've got some kind of diagram that was correct, that was worth achieved. If you've got the correct diagram and all the labels correct, that moved you up to a merit for that question. So part B firstly wanted to know what property is conserved in the collision. I guess the clue was in part A really, that we were already talking about momentum. So what is conserved here is going to be momentum, total momentum. And then it says calculate the final velocity of Alex and the bumper boat. Okay, so obviously they're both going to be together at the end. So what we need to think about here is the fact that we're going to have some kind of total momentum. We know momentum is equal to P times V. So looking at our diagram that we've got here, if we think about our vectors, P total is going to be the square root of P bumper boat squared plus P Alex all squared. So that's going to be equal to the square root of 85 times, oops, sorry, done it again, 0.5 all squared plus 48 times 2 all squared. All of that is going to be square rooted. So if you put that into your calculator, I think you get 104.99. So that's the P total. So if we want to work out the velocity, that's going to be P total divided by the mass. So we're going to have 104.99 divided by 133.85 plus 48. That gives us 0.79 meters per second. Now just remembering here that it asks you for velocity. Okay, so if we're looking for velocity, not only do we need the size here, but we also need a direction as well. So what I looked at here was the tan of the angle. The angle that you're looking for is this angle here. It's going to be 66.5 over 96. And so that gives us a theta of 24 degrees. So for this part of the question, looking at total momentum and getting your value for your total momentum correct would have got you up to the achieved level. Getting the speed correct would have got you to the merit level, and giving us a direction of well would have moved that up to excellence. It's really important that you read the questions carefully, because just the fact that you've given us a direction, which is always asked for when you're talking about velocity, has moved you straight up to the excellence level. So not particularly difficult. It's something we've just got to be a little bit aware of when we're reading questions. So then part C, we know that a short time later she jumps onto the stationary bumper boat, and she lands 0.3 metres on the centre. The bumper boat starts spinning. Okay, so now we're talking about rotational motion, and we're told it's spinning at 0.6 radians per second. And again, Alex's mass hasn't changed since the first part of the question. So what property now is conserved in this collision? Okay, now we're talking about rotational motion here. So what's going to be conserved is the angular momentum. Okay, so this time it's going to be angular momentum that we should be thinking about dealing with. Now obviously Alex is working in a linear direction, so linear momentum here is going to be mvr. The boat is spinning, so we've got some rotational motion, so L is going to be rotational inertia multiplied by angular velocity. Now if we've got conservation of angular momentum, these two values obviously going to be the same. Okay, so when we've just got Alex on her own, obviously her linear momentum is going to be this. When we've got Alex and the boat, their linear momentum is going to be this. So we know that these two things are going to be equal to each other, and what we're looking for is the rotational inertia. So if we rearrange that equation, I is going to be equal to mvr divided by angular velocity. So we know Alex's mass multiplied by the speed that she was running at multiplied by the radius, and the angular velocity that we've got is from here, so 0.600 radians per second. And you could probably even do this in your head, but this gives us an angular momentum of 48 kg meters squared. So getting to this idea here with the correct equations, looking at conservation of momentum, we've got you up to the achieved level, and actually getting the right answer was for merit. There was no excellence part for that particular part of the question. And then moving over to part D, it says explain how the period of oscillation, the period of rotation of the bumper boat would be different if Alex was moving faster when she jumped on. Well, if she's moving faster as she jumps on, she's going to have greater angular momentum, because we've said already angular momentum is mvr. So assuming she jumps in the same place, and assuming she hasn't put on any weight since she last jumped on the boat, if V is going to increase, then L is going to increase. So if she runs faster, she's greater angular momentum. So if she's got greater angular momentum, the boat is going to gain more angular momentum as she jumps on. So if we've got greater angular momentum, so if we think about this equation, if we've got greater angular momentum here, we're going to have greater angular velocity. And if we've got greater angular velocity, we're going to get a shorter period of rotation. Okay. So on this one I said there was a shorter period of rotation but couldn't really explain why. That got you to the achieved level. If you said it was because there was a greater angular momentum, that got you up to the merit level. But if you got through all of this with really good linking, the running faster, greater angular momentum means greater angular velocity, that means shorter period of rotation. With that really clear linking was what was going to get you up to the excellence level. And that was it for question 1.